All right, so we're in our last week of classes now. Um, I don't know if some of your other classes are also having to make arrangements because of the research conference that's being held in this building. I think it's tomorrow and Wednesday. And so some of the class locations are going to be switched around. For us, we'll meet in the hydraulics lab on Wednesday. So that's room 1228. And then our class meeting on Friday is just going to be a recorded video that'll be posted online. The final homework of the assignment of the semester is due Friday by 5. And then for the final exam, I wanted to remind you that you should have access to all the software packages we've used this semester because the exam is going to be comprehensive. So although the weighting of the exam will be favored towards the more recent material, meaning that proportionally more points on the recent stuff will be on the test, there may be questions from any part of the course, and so you should be prepared with HY8, StormCAD, WMS, Excel. And then you can also bring a page of notes, front and back side of a letter-sized piece of paper that has any formulas or like procedural notes that you'd like to include, but it should not include any concept definitions or terminology type question or information, because I will have concept questions on the test and definitions that you need to address, and I don't want you just to copy down what you've got on your formula sheet for that. So that's where we're at with the course. Any questions related to the announcements? Yeah.
On the final exam, will the split between conceptual and problem solving points remain about the same?
It will. It will be about the same. So that means about a third of the points will be related to concept questions, and then 2/3 of the points would be related to problem solving or some sort of a software application question. Yeah.
About the final exam as well.
Mm-hmm.
Is this going to be similar to in some past years where the final exam is, or in some other classes where the final exam might be designed for the full length of time, or is it going to be designed like a normal exam?
Good question. No, I'm taking advantage of the fact that we've got 2 hours. Normally I have to think, what can these people do in 50 minutes? So I won't be writing it with the 50-minute time frame in mind. I'll be writing it with 120 minutes in mind. And so what that'll allow me to do is ask a greater variety of questions. Rather than just only giving you a WMS problem, for example, I might include a WMS problem and a StormCAD problem. So I think it's just more opportunities so that if you are weak on one particular thing, that doesn't sink your entire final. And I won't write it so that the average student finishes in 120 minutes. I think probably those of you who are pretty quick with the software may finish in just an hour. So it'll be longer than usual, in other words. Yeah. Other questions? All right. What we're going to talk about today is groundwater, and it comes from chapter 6 of our textbook. And subsurface hydrology is a really important topic that you could have several back-to-back courses on the topic of subsurface hydrology, and here we'll only be able to spend a single week on it. So it's just to give you an idea of some of the most basic equations that you might see on the FE exam, for example, and also just to introduce you to some of the questions that get considered in subsurface hydrology. And what's significant about subsurface hydrology is that there is so much fresh water that's underneath the Earth's surface that it's a really important source of water, both for domestic use but also for industrial purposes, and even in some cases commercial use like cooling at power plants. And so subsurface hydrology would concern itself with the amount of water that's available, sometimes the quality. There are applications of subsurface hydrology that looks at how pollutants that have seeped underground will move from place to place because of the movement of the water that carries it. And just like there are important models that get used in surface hydrology to link together the relationship between rainfall quantity and runoff amount, there are also models in subsurface hydrology that would link together things like rainfall recharge and then how the groundwater table and the aquifer movement from place to place varies over time. And so there are finite element models that divide the ground and the underground environment up into a mesh, a three-dimensional mesh, and there can be different properties for each element in the mesh, and they'll assign different hydraulic conductivities, and then they'll look at the flow of water in and through those boundaries. One of the big problems that has emerged is the fact that groundwater tables are getting lower across the United States as agricultural users extract more water from aquifers than the surface is recharging. And we'll look at a couple of YouTube videos today just to introduce us to the subject of subsurface hydrology, and I think you'll notice that a consistent theme of those videos is just concern over the fact that as populations are growing, the amount of water that can be extracted from underground is declining because the areas that have good availability of infiltration are reduced. You know, when you have a lot of impervious area in a watershed, then that reduces the amount of water that can get into the subsurface, and so then that's, you know, taking the in lower than it was before. And then another aspect of it is that there is a lot more pollution getting into the underground aquifers than there was previously, and so then that sometimes makes it a challenge if you're going to use groundwater for drinking. In some past years, maybe it would be possible to take water straight from a well and put it into a distribution network, but it's becoming increasingly common that a groundwater that's under the influence of a polluted surface water has to be disinfected, where that may not have been necessary in the past. All right, so this first video is made by the Texas Water Development Board, and it talks about aquifer issues specific to Texas, which is kind of a good indicator for where a lot of the rest of the country is going, because Texas has growing populations, is, as a southern state, maybe more exposed to variability in the climate than some other places. And there are some aquifers, particularly in El Paso, where, I mean, I remember reading the doom and gloom articles about how the aquifers were just about completely used up. As much as 5-10 years ago, they said there's only 5 or 10 years left, and they're finding ways to kind of draw that out and reduce the dependency on the aquifers. But the point is, Texas has some really important issues, and if we can learn from what they're doing in Texas to manage water availability and preserve aquifers, then a lot of the other places that are less threatened can benefit from that experience that they've got. So let's watch this video. Okay, we're going to look at something similar in the slides that follow, but it's maybe not as clear as it is here, so I wanted to pause and just show you that what we're actually looking at is two different kinds of aquifers. This aquifer is confined, meaning that there is a layer that's relatively impermeable both underneath and above. And so this is just soil that has water in it. It's a conceptual diagram. If you were to actually have a side view, it would just look like soil because the water itself is clear, it's not blue. But we have, here's the ground level. Now this is soil that has some water in it, but the pores aren't fully saturated, and this is where the pores are fully saturated. And you'll notice that there's a slope to this, meaning that the water is moving towards the right for some reason. It could be that there's the recharge is occurring off the screen to the left. That's where the rainfall is, and it's emerging towards this spring, and so then that's what depresses the water level on the right. But if you go down beneath this upper confining layer, then the water is actually under pressure. And you can see that if you penetrate down through the confining layer, it may be that the water rises up above the ground level, and that would be an artesian aquifer, or it may be that there's just a little bit of pressure so that you don't have to use as much energy to pump it up into a well that you otherwise would. But this is a confined aquifer, and then what's above it is an unconfined aquifer. And so there can be multiple layers. If you go downward, 2-3 kilometers, you may pass through different aquifers that are on top of each other, and then a very thick layer of rock, and then beneath that may be another aquifer. And so we can't just think of there being a single aquifer or a single aquifer layer at any particular spot on the map, because the important regions go downward, and there can be these different layers. All right, so let me continue the video then. Okay, one of the things that it talked about in that video, just very briefly, was it talked about brackish groundwater. Is anybody familiar with that term, brackish? Let me see if I can get to the spot where they were discussing it. It just came on screen so quick. Well, here it is. Okay. These tubes are reverse osmosis units used in desalination. And brackish water is water that has high salinity, typically sodium. And a lot of that sodium comes in from saltwater intrusion. If we look at the map of the major aquifers that they've got in Texas, this Gulf Coast aquifer, you'll notice, is just up against the Gulf Coast. And when you're pumping groundwater out, then some of the water that comes back in is from the surface, infiltrating down, but also the seawater can penetrate inland. And so, especially in coastal areas, saltwater intrusion is a real problem, where if you're pumping out the fresh water, then that creates a low point in the groundwater table, and water from the sea will begin to penetrate. And so coastal communities that rely previously on groundwater can suddenly find that their groundwater is no longer fresh, that it becomes salty. And so it's not an all or nothing proposition. It's not like suddenly they find it has the same salinity as seawater, but over time the concentration of salt in the groundwater begins to increase, and there may come a point where they have to start extracting it. And so reverse osmosis is one of the approaches to do that, where they'll use high pressure pumps to force water through membranes that have very small diameter pores, and the pores are small enough that it'll allow water molecules through, but it will filter out salt. And so it's very, very expensive, and just one of the issues that they're trying to avoid when it comes to preserving the productivity of the aquifers. So if you look at the overall quantity of water on Earth, most of it is in the oceans and isn't easily used because of the salt that is in seawater. And of all the fresh water that exists on Earth, most of that is also not usable because it's in ice caps, meaning, it's fresh, but it's so far away from where the people are that it's not generally considered practical to use water that's in the ice caps, or water that's in glaciers is permanently frozen. And so most of the fresh water that we can access would be water that's relatively close to the surface. And so 0.3% of the water in Earth's environment, if we think about it as a control volume and we're looking at inside the atmosphere, where is the water that we could use, only a tiny fraction of it is closer than a kilometer to the surface. Now here's that cutaway diagram that shows the difference between an unconfined aquifer, which is the one above this confining layer, and then a confined aquifer that becomes pressurized because of the recharge that is at a higher elevation somewhere else. And so depending on the surface elevations, water can come out at the surface, and we saw in that Texas video a spring, which was where an unconfined aquifer was coming to the surface at that location. You can also have an artesian well, which would then turn into a spring from a confined aquifer. An aquitard is a formation that slows down the movement of water, but isn't as good at slowing it as like a complete clay layer might be. You know, it's possible that in the case of an unconfined aquifer like this, it could be that the water that we see here has come from the surface, but there can also be leaky aquifers. And so a leaky confined aquifer, ironically, could be leaking water upwards. So it's possible that if this is pressurized and this upper confining layer has hydraulic conductivity that's in the middle kind of zone, that the water could be leaking upward, and then this is much higher than it would be compared to if it was only just based on recharge of the ground in this region. And so we have to be aware of the possibility that water could be moving more than just down at all times, because in the case of a leaky aquifer, if you have a leaky confined aquifer, the water would be going downward and also upward as well. And just to refresh your memory about Darcy's law, which we've talked about before, Darcy's law suggests that there's this proportionality factor that describes the flow rate that can go through a packed column of soil, and it's the soil characteristics combined with the hydraulic characteristics, the difference in the head upstream and downstream across some column length where we know the cross-sectional area. And so what Darcy's law says is that the hydraulic conductivity K is what's going to be the factor that describes the total flow that you can get through some area of soil when there's a driving force of delta H divided by L. And so this proportionality factor K is also important when we talk about well equations. When we try and predict how much water can be extracted from a well based on the shape of the cone of depression, the shape of the water surface as the water is approaching a well. So this hydraulic conductivity, which we've seen before, will be an important factor when we look at the well equations. So this is a cone of depression, and I always kind of get a chuckle because I tell people about the cone of depression at the end of the semester, where maybe some people are feeling like they're in the cone of depression right now, but you'll be out of it in 2 weeks. In hydrology terms, what the cone of depression is it's the water table which gets lower as you get closer and closer to a production well. There's two different kinds of wells, a production well or an observation well. And so if you're digging a hole in the ground and you're just keeping track of the water level at that location, that would be obviously the observation well. But a production well is where you're extracting water from the aquifer at the location. And when you do, what allows you to come into an equilibrium, like a steady state, where you can turn on the pump and the water is coming out of the aquifer continuously, it has to be coming towards the well casing, and it does that from all directions. It's a radial flow coming towards the center of the well, but this flat static water table is where the water surface was before the well was turned on, before the pump was turned on at the well. But what happens is that as the water is pumped out of the well casing, then it has to be replaced by water that is in the soil. And so the water is all moving towards this central location, and then eventually there's a steady state where the rate of the water moving towards the well is the same as the discharge that's coming out of it. And let me just show you one quick point. When I talk about the radial movement of the water, if we had a well that was set up in Buzzkirk Field, maybe just one of those old-timey kind that's a hand pump, then it would be bringing water to the surface, and to be able to have more water as you continue pumping, then the water would be moving towards the well in all directions. So it would be coming, kind of have a circular influence, and the closer you get to the well itself, the lower the water table is, and that's why the water is moving from the outside towards the center, is that, remember, water flows downhill, and that's what the cone of depression is it's the downhill movement of water. And so we wouldn't see in a free surface a water surface that's quite this steep, but because it's a porous medium and water has to seep through small diameter grain voids, then we can see a relatively steep slope. And what we're able to do is measure a certain distance away from the central axis of the production well. We can find out what does the depression look like how much of a drawdown is there at a certain distance away, and then at another location. And if we have the drawdown at two locations, then we have formulas that will allow us to predict what is the rate of flow that you can get from a well by observing the cone of depression. And so, if you have gravel, the cone of depression is going to look different than if you have water that's flowing through sand, or if the water is flowing through clay. And just to illustrate the differences in materials, if you had fine sand versus coarse gravel, look at the depth of the drawdown at these two cases, which we're assuming it's the same discharge for both of them. So if we're trying to extract the same flow rate of water, what this is showing is that in a fine sand where the hydraulic conductivity is going to be lower, then you'd have to have more of a driving force to bring the same flow rate of water towards the well casing. And so how steep this drawdown is, or how far down below the static water table is that driving force, the delta H, that we saw in the Darcy law equation. And so in the case of fine sand, the drawdown is more pronounced than it is in the case of the coarse gravel. And when you have two adjacent wells that are both bringing up water, then there can be overlapping cones of depression that cause the drawdown to be even lower than they would otherwise be. And so, in both of these wells, you could see the static water table was here at some elevation below the surface. And if you just had one of the wells that was pumping, so here if you were just only pumping well A, then it would bring the cone of depression down a certain distance, but then the influence of having an adjacent well would bring it down even further. When we have wells that are extracting water, a fully penetrating well is one where it goes all the way through the entirety of the aquifer thickness. And so we're assuming that water is free to move towards the well through the entire aquifer thickness, because we've screened, meaning that there's openings in the pipe casing so that water could enter the well at all of the different elevations. The radius of the well is important because, remember, I mentioned that the equations we're going to use to predict the flow capacity for a well, they look at this drawdown at a certain radius away from the well. And one of the locations that we can measure the drawdown is at the well itself. which saves us from having to have two separate observation wells. We can have a production well and one observation well, and just with those two, predict what the flow rate is able to be based on the drawdown that we're observing. And so one of the observations would be at the well itself, and so if the casing of the well has a certain diameter, then what we would use is half of that diameter as the first radius that we're using for observation. And so this bullet point about the well radius is just important because that production well can also serve as a point of observation. Now, I've already refreshed your memory about the parameter of hydraulic conductivity, but a related term is transmissivity, which is where you take into account the thickness of the aquifer and its hydraulic conductivity. And so here, whether it's a confined aquifer or an unconfined aquifer, both of them, you could talk about the transmissivity of the aquifer, and K has units of length per time. So hydraulic conductivity would usually be centimeters per second or meters per day. It's a speed, in other words, where the aquifer thickness is going to have units of length, and so transmissivity is a flux. It has units of length squared per time. And so it would be meter squared per day or centimeter squared per second, potentially. But we just simply multiply the thickness of the aquifer by the hydraulic conductivity, and then we get the transmissivity, which will go into the equations we use for trying to describe the shape of the cone of depression. We've talked about hydraulic conductivity, the thickness of the aquifer, transmissivity. In a confined aquifer, we're not actually observing drawdown of the physical location of the water, but we're observing drawdown of the piezometric head. And let me just, I don't have a marker. Let me go to this side view of this aquifer. So if we started to extract water from one of these wells pretty consistently, then if it's an unconfined aquifer, you'd see the physical location of the water starting to draw down. But in an confined aquifer, it won't be the water surface that draws down at first. It would be simply a reduction in the pressure of the water that's surrounding in the vicinity of the well casing. So this term here, the piezometric pressure, is the sum of the elevation and the pressure head at a certain location. And so inside the confined aquifer, you'll remember back to fluid mechanics, we talked about piezometers and how a piezometer, if you connected it to a pipe, is a way of measuring the pressure, and you're puncturing the pipe and allowing the water level to rise to a certain elevation, which represents how much pressure there is inside the pipe. And so the same thing is true with an aquifer, that you can puncture it, connect a tube of some sort, and the water level will rise, indicative of the pressure inside the confined aquifer. So it will be that piezometric pressure which is reduced in a confined aquifer, where it's the physical water height that will be reduced in an unconfined aquifer. And you'll remember the difference between porosity and effective porosity, that some pores may not be interconnected, and so although a given soil may have lots of voids, it's the interconnected voids that are effective for porosity that we have to keep track of when we're talking about movement of water through the subsurface. Okay, so this is what we'll look at for today, is just a confined aquifer. And the confined aquifer equations here, we have a piezometric surface, which is the height that the water would rise to if we puncture the confined aquifer. And you can see that the piezometric surface is getting lower and lower in the direction of flow. And so here, this is the surface, and then a confined aquifer, which means that there's a confining layer both above and below this region, which is allowing the water to flow more freely. You know, the hydraulic conductivity through this confined aquifer is much higher than it would be through the confining layers. So here B, the height of the aquifer, is going to be one of the important parameters that goes into transmissivity. And this equation describes the flow rate that you can get out of a well based on the transmissivity, which is the height of the aquifer multiplied by the hydraulic conductivity. And then H here is the height of the water surface if it would rise to a certain level in a piezometer. And sometimes what's confusing is that it will, in a problem like this, it'll describe the drawdown. And so here, S, the drawdown, is the difference between where the water used to be when conditions were static and there wasn't any water coming out of the production well, so the initial water surface height, and then the cone of depression that sets up in equilibrium. So in other words, if H is the starting height of the water, then H minus the drawdown S gives you the height of the piezometric head at a certain location. And so H would be the height of the piezometric surface above the bottom of the confining layer. And then R is just the distance away from the center line of the well. And in this formula, it's really important that location 1 is closer to the center of the well, and location 2 is the one that's further away. Because this is a logarithmic function, it doesn't work if you switch those and would have a the further distance as the location 1. So what this will describe is either the shape of the water surface on the top equation, but more usefully on the bottom equation, what we could do is if we know the flow rate and we know a couple of locations, then we can predict what the height of the water would be at that spot. You can use this well equation to infer what is the hydraulic conductivity if you know both the radius, the heights, and the flow rate. So then the only unknown would be transmissivity, which is related to hydraulic conductivity. So this is a really useful equation and one that I've written lots of questions on the FE exam related to flow through wells. So if it is a confined layer, it's called the theme equation, and this is what it looks like in one of the previous versions of the FE review manual. It's just basically the same as this other slide. I wanted to show you that it is in there. Let's take a look at this example. We have just 9 minutes remaining, but let's see if we can get the first of these two questions. It says we have a confined aquifer with a hydraulic conductivity of 20 meters per day, so that's K, a thickness of 6.6 meters, so that's B. So we know K and B and multiply the two together and that gives you T. An initial piezometric surface of 14.53 meters above the lower confining layer, so that's H, is 14.53. And we're trying to solve for what is the flow rate Q that would cause the piezometric surface to be 13.85 at a radius of 40 and 14.31 at a radius of 85 meters. Okay, so this is not describing it in terms of drawdown. This is describing it in terms of the H, so that's just easier for us. We don't have to calculate H from the drawdown. So what we're saying is location 1 is the one that's closer together, so that's radius of 40. So R1 is 40, H1 is 13.85, and then R2 is 85 meters, and H2 is 14.31. Okay, so with these parameters described, we know T is K times B. We know H2, H1, R2, and R1. Let's find out what is the flow rate that would be required to cause the drawdown that's described in this problem statement. So let me pause for a second and give you a chance to see if you can use the theme equation to calculate the flow rate. Okay, so this is talking about the piezometric surface. It's not talking about where the water is going to be, because the water is going to stay through the whole thickness of this confined aquifer. It's just that the pressure is going to be decreasing in the direction of flow. And that's why the water is moving towards the well casing, is it's high pressure further away, low pressure the closer you get towards the screened well. And by screened, what it means most of the time, let's say this is a PVC pipe, there's just small little perforations in the PVC pipe. You know, it could be holes that are maybe 1/2 millimeter in thickness that have been sliced into that pipe, and it allows the water to seep in to the well casing and the soil will stay on the other side of that. Okay, so doing the substitutions here, 2 pi times the transmissivity, which you can see 132 meters squared per day, and then the difference in the height of the piezometric surface. I got 506 cubic meters per day. Did anybody else get that same value? See a couple of nodding heads. All right. 12:49, we're out of time for today. When we get together on Wednesday in the hydraulics lab, we'll get the second part of this confined aquifer question, and then we'll also discuss unconfined aquifers. But just to look at the announcements one last time, you've got one more homework assignment, which is due Friday at 5, and then starting to think about the final as well. All right, so I'll see you Wednesday over in the hydraulics lab.